Can you folks hear me good?
Yes.
Yeah.
Okay. So how many people are sick? Nobody, right? I mean, like with the virus, not like, you know, mental issues or something.
And definitely mental issues.
Yeah, that would include everybody, right? So, okay, so one thing, you can go and mute and unmute yourself. You can show video or not show video. And there's also a chat function. So I don't know exactly what it looks like on your end, but sometimes at the bottom of the screen, if you put your mouse down there, you'll see a place for messages. Okay, so for example, I type a message here. Can you guys see that?
No.
No.
It's called chat. There's a chat function. It should be at the bottom of the window.
I'm using my phone for this.
Do you have a computer?
No, I do not. I borrowed one from the library, but I'm not using that one right now.
Okay. Yeah, some people, yeah, most people are seeing it now. Okay, so.
Oh, I see it. But how do I? Oh, okay, I see it.
Good. So, just out of curiosity, how many other courses do you have where the faculty members are using Zoom? Anybody?
I have one other class.
One other class is using it?
Yeah.
Okay. And are they trying to teach like a regular lecture type of class or just the interact?
Yeah.
They are?
It's like a regular lecture kind class.
Okay. So there's a free Zoom. And then the university got some deal with Zoom. But then, so that's what my journey was, right? First I got the free Zoom. Then I did it through the university where you get a little bit more features. Then I just found out this morning that there's a pro that you have to apply for as a faculty member. So I might be missing certain features. Like I can't figure out how to do screen sharing right now. But I've been on Zoom meetings every day for the last 2 weeks. Friday, we had a master's proposal defense totally on Zoom. It worked really, really well. Anyway, I don't have anybody to help me figure this out. There's no one in the building. So first, what are your concerns? What's your major concerns? I mean, beyond getting sick and everything, but you know, about the class.
Yeah, I have a question.
Uh-huh.
It says on the testing center website that after April 6th, the testing center is going to be closed. How are we going to take our exams?
That's a good question. So hopefully we'll bang that out tomorrow. So I'm on this task force. It's a system-wide task force. So it's like me and about maybe 15 people. One of them is the vice president of the university. He's in charge of academics. We have the head IT person for the university system on there and a whole bunch of other people like that, librarians and stuff like that. So this has been a concern that I've been raising for ever since we started having these meetings. What about the testing centers? So the test centers want to close just like everybody else. They don't want to get exposed to any viruses. But then we don't have testing centers. You're exactly right. How are we going to do the exams? So a lot of discussion going on, and yeah, hopefully we'll find out tomorrow.
Okay, thank you.
All the faculty are really worried about this. So any other major concerns? Anybody lose their job?
I did.
Yeah.
A couple of you did?
Mm-hmm.
Yeah. So there may be some financial help, and we're still working on that. So you might want to go to,
Like through the school?
yeah, through the university. You might want to go to, like, you know, on the La Lima site, when you first open La Lima, at the top there, there's this like COVID-19 whatever, and there might be some information there. Okay, the website for the university on this disaster is has a lot of information on it. And so one of the people who's doing all that is on that group that I meet with every day. Except today we didn't meet. So is anybody worried about having to drop course because of financial problems? No? Okay. So one thing I could just try to get across again. So when I started writing this book, I tried to make it like work, right? So you start from the beginning. There's some problems to try to develop the idea. Then you go to the next thing, maybe the next level of difficulty, and then there's some more problems. And oftentimes there's problems at the end of those sections that, and they're all worked out problems. And so if you start from the beginning and just work through it with that mentality, you should be able to learn the material. But what I find is that students don't read the book. They want to go to Google something to find a video that tells them exactly what to do, so they don't have to read anything. Or they wait until they get to a homework problem, and then they just look through the chapters trying to find something that matters. In other words, they're avoiding the learning process.
Somebody has to mute themselves because we can't hear you.
Say again?
Somebody, I hear
James.
other background.
Yeah, James, mute your stuff. Mute your thing.
Why should I do this?
James, Sal, mute your thing.
Whoever has kids in the background
There's a stain.
needs to mute their mic.
There's a stain. I can't read a lot. That's why you do like this. I did do that.
Not that I hate kids, but they do grow into teenagers. That is a problem. Okay. So what was I saying? Oh yeah. So the whole idea is you go and you read the chapter and you work through the problems. Then the quizzes are designed to go through really basic kinds of problems and explain things as you're doing them. So that's another learning process. So you should do the quizzes and then do the homework. And what I'm noticing is just the opposite. students are doing the homework, and then if they have time at the last minute, then they'll go do some quizzes. Or they even try to do the quizzes after the exam, which is totally defeating the purpose. Does that make sense to you folks? So read the chapter, do the quizzes, and then do the homework. And by that time, you should be more than ready for the exam. But if you start spending all your time hunting around on Google trying to find the magic video, it's not going to happen. If you do find good videos, you might want to refer that video to other people, right? So, yeah, and you do know that I do have that YouTube site with all my videos on there.
It's missing chapters though.
Well, I don't do it for every chapter because here's how ghetto it is, okay? Let's see if I can do this. You see this? This is my production studio. It hangs over this thing right here like this, and that's how I do it. It's more than ghetto. And it takes a lot of time. So I'm not going to make videos for every single topic. What I'm going to make videos for is for the more difficult topics. See, again, you're looking for videos to solve all your problems, so you don't have to read and you don't have to do problems. In your mind, you're thinking there's going to be a magic video, and there's not going to be. So you have to read the chapter, you have to do the problems, you have to do the work. You should do it in the sequence that I tried to explain. So, any other concerns? So, what about the material now? There's chapter 10, 11, and 12. So chapter 10 is basically how to do Lewis dot structures, how to figure out the shapes and bond angles, right? And there's very, well, there's a really long video. There's like a 45-minute video and then another 15-minute video and stuff like that. And then students are complaining, oh, 45-minute video, that's too long, we can't watch that. Except there's a thing called pause, and then you can resume it, right? So looking at that, so here's a model here, right? So how many regions of electron density do we have?
3.
3, right? How about this?
3.
3 regions of electron density. And so the shape of this molecule is planar and trigonal, right?
Mm-hmm.
So you have 360 degrees in a circle. If you divide it into 1, 2, 3 pieces, each of these angles right here is 120 degrees. Make sense?
Yep.
This is how simple it is, okay? Just because it's called chemistry doesn't mean it's more difficult. Now, if I take one off, it's not planar trigonal anymore. What's it called?
Bent.
Linear.
Bent.
Oh.
It's bent. And the bond angles are still 120 degrees. See this model here? The way I have it now, this makes no sense at all. Because electron clouds repel electron clouds. So if there was only 2 regions of electron density, this thing would be linear, like this. It's because of this non-bonding electron pair pushing away these other electron pairs that keeps it to be 120 degrees. That make sense?
Mm-hmm.
See, this is just like lecture. You know, you ask a question and you don't get much response. Now, if I take off another one, what's the shape of this?
Diatomic.
Diatomic, exactly. There is no central atom. So there are no regions of electron density. It's just diatomic. It doesn't matter whether these are there or not. It's still going to be diatomic. Okay.
What's it called?
Sorry?
What's the structure called? Diatomic?
Diatomic. This simply means two atoms. What about this one?
Tetrahedral.
Tetrahedral.
Tetrahedral, right? So it's because the solid shape has four sides, right? So here's one side, two sides, three sides, four sides. So tetra means four. So tetrahedral. And then a tetrahedral, which has, you know, 3 dimensions, not like the other one, which is only 2 dimensions. 3 dimensions, so this bond angle right here is greater than 90, it's 109.5 degrees. It's like if you take your fingers and go as far apart as possible, you get that. It's about the same thing. See that? So 109.5 degrees is tetrahedral. So if I take one off, do the bond angles change?
No.
No, still 109.5. But this shape right now is called pyramidal. Like a little pyramid. These
What did we
three
call-
right here are pushed down because of that non-binding electron pair that's there.
Would
Otherwise,
it still be classified as tetrahedral pyramidal or just pyramidal?
I just use pyramidal.
Okay.
Okay. So you see the difference between here? This one is flat because there's no electrons right there, right? This one is not flat because of this electron pair right there. So now, does this make sense?
No.
Does not make sense because the only reason why they would be bent down if this was there, right? Does this make sense?
No.
No, because this non-binding electron pair would be pushing these other electron pairs down so to make it have depth. So that doesn't make sense. This does. This doesn't make sense. But that does, right?
Mm-hmm.
So now if I take off another one, what's this shape?
Bent.
Bent?
It's bent. Exactly. Okay. So what makes it bent is those non-binding electron pairs. So does this shape make sense?
No.
No.
Because that would be linear, right?
Mm-hmm.
So I'm trying to get you to the point where you're looking at this as common sense. Science is common sense. Now, if I take off one more atom, what's that shape?
Diatomic.
And it's still bent.
No,
Is it diatomic?
it's diatomic, right? There's only 2 atoms there. There is no central atom. So we just covered the major shapes. I think I'm not going to do the more complex ones with 5 and 6 reds at this moment. Then, what about symmetry? Is this symmetrical?
Yes.
Symmetrical. So if these bonds were polar covalent bonds, in other words, there was a dipole there. If the difference electronegativity between this atom and that atom were greater than 0.5, meaning that they were polar bonds, right? Then they behave like little rockets. So what would happen if I fired all 4 of these rockets all at once? Where's it gonna go?
Nowhere.
Nowhere, exactly. So this is a non-polar molecule. This molecule does not behave like a little magnet, like water. Remember water? Water behaved like a little magnet. So this would not dissolve in water. It would more likely dissolve in oil. Now, I take one off. Is this pyramidal molecule symmetrical?
No.
It's not. So now if I have 3 rockets and I fire these 3 rockets, it's going to move somewhere, meaning that it's a polar molecule. So this molecule would dissolve in water. That makes sense?
Mm-hmm.
Yes.
So you're saying that if it's not symmetrical, then it won't be polar, a polar molecule.
If it has polar bonds.
Oh, okay.
If it has only non-polar bonds, then it has no hope of ever being a polar molecule.
Okay.
So now, here is the example of water. So is this a symmetrical molecule?
No.
So there's a rocket here, a rocket there. If you fire those rockets, it's moving somewhere. So if these are in fact polar bonds, then this is a polar molecule. This was the example of water. The water molecules are attracted to water molecules, right?
Yes.
Because they both act like, how do you say, little magnets. I'm trying to read the, I'm trying to read the chat at the same time. Yeah. Okay, what about this one now? Is this symmetrical?
No.
It's asymmetrical, right? So if this is a polar bond, it's a polar molecule. If it's a non-polar bond, then it's a non-polar molecule. So here's another twist on it. But what about this? Symmetrical or non-symmetrical?
Symmetrical?
What if the green bonds were polar and the white ones were non-polar? Then I would have 2 rockets,
Asymmetrical.
2 non-rockets. So it would move, right? So it's asymmetrical. The polar molecule in that case.
What would that molecule be called?
Well, we don't know what the atoms are, so we don't have a name for it.
Okay.
But the shape of this would be tetrahedral.
And since there's polar and non-polar covalent bonds, then it would be
Yeah, be a polar molecule.
Oh, okay.
So what if what about this one? Symmetrical? Symmetrical.
Yes.
Symmetrical.
Symmetrical, right? Now let's say these were non-polar covalent bonds. Then obviously it's going to be a non-polar molecule.
Mm-hmm.
But let's say these were polar covalent bonds. So each one of these is a dipole. Still going to be non-polar, isn't it?
Yes.
Because if I fire all these rockets at one time, it's not going to go anywhere. Those forces just cancel each other out. So this would be a non-polar molecule, not dissolve in water, more likely to dissolve in oil. See how the symmetry has something to do with everything?
Yeah.
What if I told you that there is a molecule X, and molecule X dissolves in water? Is molecule X polar or non-polar?
Polar.
Polar.
There you go. So say we're going to make some household cleaners or something, right? So we take some ammonia and we dissolve it into water. We take a little bit of blue dye, dissolve it into it, then a little bit of soap and dissolve it into there. And we call it Windex. Is every single molecule in that container of Windex a polar molecule?
Yeah.
Yes.
Right.
They're connected to each other.
Okay. What about this molecule? Symmetrical or not?
Symmetrical.
Symmetrical, right? So if these were rockets and I fired all those rockets all one time, it's not going anywhere. These two would simply counteract those two and go nowhere. So here we have two central atoms. The two black ones are central atoms, right? So the central atom has how many regions of electron density around it?
3.
1, 2, 3. So double bonds simply are red. Triple bonds are simply a red, right? A region of electron density where you find electrons. And we treat them the same. So these guys are going to repel each other. And then look at this shape at this central atom. It's planar and it's trigonal. And the bond angles would be 120 degrees. Same thing with this one, right? Make sense?
Yep.
What about this now? Is this one symmetrical?
No.
Asymmetrical.
Asymmetrical. So now, what if this were a polar bond? The other three were non-polar. It would be a polar molecule, right?
Mm-hmm.
Okay, this molecule has two central atoms, right? So this central atom here has how many regions of electron density? Only 2, right? one over here, which is a single bond, one over here, which just happens to be a triple bond. So to get this red as far away from that red, they're going to be 180 degrees apart. So this is a linear molecule right here. Same thing on this side, right? 2 regions of electron density, 2 regions of electron density. You want to be as far apart from one another as possible. And that's how you do it. So this is linear. So is this a symmetrical molecule?
Yes.
So it's going to be nonpolar. Is this symmetrical?
No.
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 So what if this was a nonpolar bond and this was a nonpolar bond? In other words, there's no polar bonds. Then it's going to be a nonpolar molecule. What if this is a polar bond and this one is not?
It'll be a polar.
It would be polar, right? The rocket, and there's nothing there to counteract it, then it's going to be a polar molecule. Let's see. So I'm assuming this is helping, right?
Yes.
Yes, it's helping.
So this is the kind of thing that I wanted to do instead of doing just repeating a lecture. You know what I'm saying? Yeah. I can go into the more complex ones. So Chemistry 100 students don't have to do the more complex ones. You only have to do 4 reds and but the biochem classes have to do molecules that have 5 and 6 reds. But even though they do not meet the octet rule, they still exist. Okay. So this one has 5 regions of electron density. You can see 3 of them are there, and 2 of them are here, right? So we could say that these 2 right here are axial. They're exactly 180 degrees apart from one another, which is the most stable you can get. These ones, on the other hand, is planar trigonal, where this is linear. So the planar trigonal ones have a little bit more things to deal with. So they have repulsion from this electron cloud, that region of electron density, this one, and this one. So this is the most complex shape because there's 2 different kinds of atoms, right? The axial, equatorial. When I was doing these other ones, it didn't matter which one I took off first, but this one it does. So if I take off one of these axial, one of these equatorial ones, it's a little bit more stable. So if I take one off, this symmetrical?
No.
No. If all of these were polar covalent bonds, in other words, difference in electronegativity greater than 0.5, these 2 would simply counteract each other. But these 2 over here would be spinning this molecule in a direction, making it a polar molecule. But if none of these bonds were covalent, then it would be a nonpolar molecule. Anybody remember the shape of this? I can use my cell phone for this. Does that help? Seesaw. Somebody had a sense of humor way back when they were figuring this stuff out. I was like, oh, it's a little seesaw. I might have been the only chemist that had a sense of humor in the history of chemistry, but whatever. Now, if I take off one more, I'm also going to have to take off from the equatorial. Is this symmetrical?
No.
What's the shape? That way it looks like a T, right? So I always say, oh, Mr. T, like, you know, the now very old movie star. So if these bonds were polar, these two rockets right here would exactly cancel each other out. But there's nothing there to cancel this one. So this thing's going to move. So therefore, it's going to be a polar molecule. If covalent bonds, then they're going to be nonpolar molecules. Now she can, I can mute people, but I think it's kind of rude, but anyway. Now, if I got one more to take off, you can see these axial ones are as far apart as possible. But this one has interference here and here, so I'd be taking off this one. So the shape of this is going to be linear. The central atom has only, well, it has got 1, 2, 3, 4, 5 reds still, but there's only 2 that have bonds, right? So it's linear. Is it symmetrical?
Yes.
Polar or non-polar?
Non-polar.
And it doesn't matter whether these bonds are polar or not, because if it's symmetrical, they're going to cancel out even if they are polar.
So if it's symmetrical, then it's non-polar.
Exactly.
Mhm.
No matter what. Now, if I take off that one, it's no longer, well, it's diatomic now, right? See that, diatomic? There
Mhm.
is no central atom. So if this is a polar bond, it's a polar molecule. If it's a nonpolar molecule, then it's a, excuse me, nonpolar bond, then it's a nonpolar molecule. And that's the most difficult one. So, put this back together here. So, I got 3, 4, 5 regions of electron density, right? So the shape of this is called hexahedral because there's 6 sides. So 1, 2, 3, 4, 5, 6 sides. Another name for this is trigonal bipyramidal. So here's one pyramid, here's another pyramid. Okay. So the molecule that I just put together, is it symmetrical?
No.
No.
So it could be a polar molecule. So if this red bond right here was polar and all the white ones were non-polar, you can see that would be a polar molecule, right? And it would dissolve in water. Okay. As it turns out, the most complicated of them is simply the simplest. Okay. So this is octahedral. So you got 1, 2, 3, 4 sides on the bottom, 1, 2, 3, 4 sides on the top. Okay. Another name for this would be square-based bipyramidal. 1, 2 pyramids. Okay. So right now, this molecule is symmetrical, right? So it's going to be nonpolar. And the bond angles are 90 degrees, 90 degrees, 180. That's all there is. So there is no axial and equatorial. It's just, they're just all the same. Now if I take one off, now it's not symmetrical anymore, right? Bond angles are 90 and 180, it's not symmetrical. If these are all polar bonds and I fire all those rockets all at once, this thing's gonna move. Because there's nothing over here to counterbalance it. And the name of this shape is square-based pyramidal. So square-based bipyramidal was one of the names for an octahedral. So this is bipyramidal. This is only pyramidal now. Now if I take the other one off, I get this shape. Symmetrical?
Yeah.
It is, right? So because it's symmetrical, it's going to be a nonpolar molecule. If all of these were polar covalent bonds, little rockets, and you fire all those rockets all at once, it's not going to go anywhere. These guys counteract each other. These guys counteract. This is called square and planar. Now, if I take off another one, this is called Mr. T again. And it's asymmetrical, right?
Mhm.
So this molecule could be polar. If these are polar bonds and it's not symmetrical, then it's going to be a polar molecule. These two rockets right here counteract each other, but there's nothing to counteract this one. Take off one more. What's this shape?
Linear.
Linear, right. Okay. So I got 4, 5, 6 reasons of electron density, but it's still linear. And it's symmetrical, isn't it? So it has no hope of being a polar molecule because it's symmetrical. Now if I take off one more, there's no central atom. So what's the shape?
Diatomic.
Diatomic, simply 2 atoms, right? Is it symmetrical?
No.
No.
So it could be polar or non-polar depending upon what is the difference in electronegativity in that one bond. Say this electronegativity difference was 0.4. Polar or non-polar?
Non-polar?
Non-polar.
Non-polar.
Because the threshold is 0.5, right? So if it's 0.51, then that makes that a polar bond. And there's nothing to cancel that out. So it's a polar molecule. It would dissolve in water.
So the threshold for polar or non-polar would be 0.5 or
Yep, 0.5, right.
okay.
Yep, that's in, yeah, I wish I could do the screen share. I did all the settings right and everything, but I don't know whether I need to get the professional version of this or I just don't know what I'm doing.
You're supposed to be on chapter 10 molecule structure.
I can see you scrolling through the chapter 10.
Yeah, I can see it too on your screen.
You can see this that's moving around right now?
Yeah.
Yeah.
Why do not I see it then? What's wrong with you people? I thought you couldn't see that. Okay, so let's see. Okay, where is that part on electronegativity? I hope I'm not making you dizzy. Oh, here it is. Okay. Okay, so if it's between 0.5 and 1.7, then it's a polar covalent bond. And we use the partial charges. And we call it a dipole because di means two, right? It's like a car battery. Any battery is a dipole. It's got two ends, a positive end and a negative end. And that represents potential energy. And if it's greater than 1.7, we'll just call it an ionic bond. If it's an ionic bond, then we draw it, its Lewis structure, like it's an ionic compound. So, let's see. So here's a bunch of organic molecules. So one thing I was hoping to do is like just kind of go through here now that I think you can see it, and you tell me what part is confusing to you and what part is not, so we can get confusing things disconfused. What about the cursor? Can you see the cursor there?
Yep.
Yep.
Really? It's crazy. I can't see the same thing that you guys see. So if we're looking at ethanol, this is the thing that, you know, adults drink to forget about their children and things like that. So this part right here, look at that oxygen right here. That's got 1, 2, 3, 4 regions of electron density, right? Here's something with 4 regions of electron density. Now, two things off, 2 bonds off. What's that shape?
Bent.
Bent, right?
It would,
What's the shape of this ethanol functional group right there at that central oxygen?
Wait, what?
Yeah, what's the shape at the central oxygen? It's got 4 regions of electron density.
And
Some have atoms, 2 of them don't.
It's bent.
Please say bent. Thank you. Chemistry teachers have to do a lot of begging. Please say bent.
Int.
Thank you. So now, if I'm looking at this OH right there, that's a polar covalent bond. And I'm looking at this CO right there, that's a polar covalent bond. All the carbon-carbon is non-polar, and all the carbon-hydrogen is non-polar. See how I put the different electronegativities over there? So what is it that makes ethanol dissolve in water?
Polar.
It's that COH group, isn't it? That makes it dissolve in water, because that's a polar part of the molecule.
I have a question though.
Yeah.
So is it only carbon and nitrogen can only have 4 covalent bonds, correct?
Well, in general, nitrogen likes to have 3, but can also form 4, right? And there's other combinations as well. So again, it kind of goes back to the previous unit where you're looking at how many bonds do they want to make to get like a noble gas in general. But then there's always exceptions, right?
Mm-hmm.
Make ethanol molecule. I'm just hoping that you're all over 21. So here's an ethanol molecule. So here's the CH3, right? Oops, I need one more hydrogen on there. Here's the CH2. Here's the oxygen. Here's the hydrogen. And these are the non-binding electron pairs on the oxygen. So all this part over here is non-polar. All this part over here is polar. So because there's so much of the molecule that's polar, it dissolves readily in water. So proof is about twice the alcohol content. So if you know any adults that drink, say, wine, and it says 12% alcohol by volume, what that means is about 24 proof. Here, on the other hand, is about 5% alcohol, so it's about 10 proof. Rum 151, that's 151 proof. So it's about 75% alcohol. If you take alcohol and water and make it at least 70% alcohol, it will burn if you put a match on it. So what does this do when you drink it? You act kind of dumb, right? It makes you oftentimes say the wrong thing to the wrong person in the wrong place at the wrong time. But it does turn you into the best race car driver that was ever on the road. So it's called the inebriating solvent. So if you drink this, you have an enzyme in your blood called alcohol dehydrogenase. What it does is it takes this away. Double bond here. Like this, and that's the next molecule that's underneath there. It's called acetaldehyde or ethanal, and this is the molecule that gives you a hangover. And so, yeah. So if you have a hangover, what do you do to get rid of the hangover? You need to get this out of your body. There's no other way around it. Get it out of your body. You need to drink a lot of water, and it goes out through the urine. You can also sweat it out and things like that. But regardless, this is what gives you the hangover. I'm looking at this central atom right here. How many reasons of electron density do we have here? Right there.
3.
So around this central atom is planar trigonal. Bond angles 120 degrees, right? Is it symmetrical right here?
Yep.
No, because all three of these things are different around that central atom. So it's asymmetrical. Okay. So what if I told you this was a polar covalent bond? That means it's going to be a polar molecule, right?
Mhm.
So does ethanol dissolve in water?
Yes.
Yes, it does. Now, we don't do this, but if we oxidize this one more step, we react it with molecular oxygen, we can get this. Ah. Sorry. This is the one right below that. This is called acetic acid or ethanoic acid. So we already talked about this one. That hasn't changed much, but this one here is changed. So this central atom right here has 4 reasons of electron density, right? 2 have atoms on it and 2 don't. So what's the shape of this oxygen atom right here?
Bent.
It's bent. That's a polar covalent bond, that's a polar covalent bond, that's a polar covalent bond. Is it symmetrical?
No.
Asymmetrical. It has polar covalent bonds, soluble in water. It's a polar molecule. So vinegar is about a 5% solution of this. Okay. So it's interesting that in science, we have rules, and students tend to think that, oh, well, if it's a rule, you can't break the rule. Every time you have a rule, there's going to be exceptions to the rule. And it's the same way in the law, right? There's a law. It says, oh, if you break this law, then you go to jail. But then the court always has mitigating circumstances, and the lawyers get involved in everything else, right? So there's always exceptions to everything. And so you're not responsible for these exceptions. You just need to know that they do exist. So the difference between my approach to chemistry and other people's approach is like, oh, this is hard. Some people are like, oh, this is hard. Just ignore it. Me, I'm going right into it and I'm showing it to you. Okay? Because I want you to see the reality of it. But it won't be on a test or anything like that. So going back to these expanded octets, do you expect to go find these out in the playground? The answer is no, because they're too unstable. But as a chemist, if I take two stable things and put them together, are they ever going to do a chemical reaction?
No.
So you need to invent unstable molecules so that you can get chemical reactions to actually happen. You guys ever watch Breaking Bad? Yeah. You guys got plenty of time on your hands now, right? So, you know,
No, not really.
No, we do not.
why? Because of kids or something?
Kids, 5 classes, and then my son has classes now since he's not in daycare.
Yeah.
Every morning at 9 o'clock.
Yeah. Yeah. Anyway, so if you do get time, you should watch Breaking Bad. I think it's one of the best shows ever. Okay, I'm going to close that and probably never figure out how to get the next one up. Do you see that?
Yep.
Yes.
Yes.
Yeah.
Wow, this is amazing. Okay. So this is kind of like a little review right there. View of the bond angles. And I went into expanded octets. And so here's a new concept, it's resonance. So let's see. When you're writing the Lewis dot structures for some molecule, and you have to put a double bond in order to meet the octet rule, which by the way, the only time you ever put a double bond is if that's the only thing you can do to meet the octet rule. But some molecules like this, you could have put the double bond here, or you could have put the double bond here. Same thing over here. So if I hold this one steady, I can have a choice of putting the double bond here or putting the double bond here. But I could have done it this way, put the double bond down here. So even though we can draw two different resonance structures like that, they turn out to be the same. Because this is not truly a double bond, and this is really a single bond. Electrons don't care about double bonds, single bonds, and triple bonds. Electrons don't have a brain, okay? So they don't care about humans because they have no way to know that humans exist. So they just do what they do. We talk about double bonds and single bonds and S2P6, all this kind of stuff. This is a human construct. It's an accounting method that helps us figure things out.
When would you ever put a triple bond?
Here's one. We had to do that to meet the octet rule for these two atoms right here.
Okay.
Okay, that's the reason why. I go through the different ones over here. But yeah. So as it turns out, electrons don't care about single, double, and triple bonds. So because these can be drawn both the same way, we say that they're the same. That's not truly a double bond. It's not truly a single bond. This is more like somewhere between a double bond and a single bond, and same with this one. We like to say that, oh, each of these bonds is the same, and each bond is about 50% double bond character and about 50% single bond character. Make sense? Going back, is this a symmetrical molecule?
Yes.
Symmetrical.
It would be nonpolar, right? Yeah. So instead of just like showing you one or two and then like saving a whole bunch for the exam or something, I just showed you pretty much everything. I think it's more important to see everything than to just reserve things for an exam or for a problem or something like that. So I pretty much put them all there. And then the whole section over here is about polyatomic ions. So when we did naming in exam 3, we just had to memorize their names. But what I did with this section over here, try to get you familiar with them so you have some understanding of where they're from. And at the same time, I get to show you all the Lewis dot structures for them. So here's the ammonium ion. It comes from ammonia. Okay. And here's what happens when ammonia is put into water. See the difference in electronegativity I put there? But why did I put those partial charges? Because electronegativity is greater than 0.5. So there's a dipole here. And oxygen is more electronegative than hydrogen. So electrons are being pulled from the hydrogen towards the oxygen. So I put a partial negative on the oxygen because it has more electrons, and a partial positive on the hydrogen because it has less electrons. The net charge is still 0. It's just that the electrons are not shared equally. Now, you're not supposed to use psychology when you're talking about science, but I do it anyway. So look at that hydrogen atom right there. Hydrogen had 1 electron of its own, and what it wanted to do is get 1 more electron so it could pretend to be 1s2, because that's stability, right? Like helium. So it shared that electron with oxygen to become 1s2. But now, is that a good relationship? It expected to share the electrons equally so they could both be happy. But what's happening is the oxygen is pulling the electrons away. That hydrogen right there is not as happy as it could be. Then, here's an ammonia molecule. So you see the partial negative right there? Partial positive would be on the hydrogens. That partial negative is on that non-binding electron pair. So if you look at this hydrogen, what it's thinking, okay, this oxygen is trying to take my electron away. And here comes another molecule that has 2 electrons, which I want, and it's not even using them. So every so often, this hydrogen right here is going to say, you know what, you can have my damn electrons, I'm out of here. It leaves as the H+. So the H+ comes over here. You see that non-binding electron pair now becomes bonding. So now the ammonium ion has 4 reasons of electron density, but it has now 1 proton more than it does electrons. That's why it gets that positive charge. And you see these blue bonding electrons in the water? When the hydrogen leaves, it leaves those 2 electrons behind. Now the hydroxide ion has 1 electron more than it does protons. And that covers 2 of the polyatomic ions right there. Windex, by the way, is a dilute solution of ammonia. And in the solution itself, you have more than water, you have more than ammonia, you also have the ammonium ion and the hydroxide ion, what makes it a much better cleaner and a much better disinfectant. So would Windex kill the coronavirus? Yes, maybe not very quickly, but it would. Matter of fact, any alcohol would dehydrate. Any acid or base would disable it. Anyway. So where does ammonia come from? Here is an amino acid. This particular one is called serine because of what's over here. All amino acids have this whole part here in common. The different amino acids have different things down here. Okay, so you eat protein, you digest it into amino acids. Now what happens to each of those atoms? The carbon goes off as CO2, and you can see CO2 right here. The hydrogen goes off as water for the most part, and the nitrogen, which is over here, is cleaved off over here by an enzyme and ends up as ammonia. But ammonia is toxic. This is why you have the urea cycle. So the urea cycle is mostly in your liver, and what it does is it takes ammonia, which is a waste product from eating protein, and it takes carbon dioxide, two waste products, and it uses energy to convert it into urea. Because urea is much less toxic. Make sense? I'm a biochemist, so that's my perspective on things. If chemistry for the sake of chemistry, it just bores me, okay? But using chemistry as a tool to understand biology is probably the most exciting thing in science. Anyway, so here's a molecule, ammonium ion and the sulfide ion, right? A monoatomic ion and a polyatomic ion. So I don't want to spend much of time doing this stuff, but that's kind of the idea, right? About this part of the chapter. And another thing that I'm doing here is showing you acid-base stuff. By the time we get to Unit 5 and we're covering acid bases is going to be a review for you. Like, oh, okay, we understand that part already. So anyway. So here's the acetate ion. And again, if you look at the formula for acetic acid, it's this right here. See that? The hydrogen in front. Whenever the hydrogen is in front like that, they're telling you that that is an acidic hydrogen. That hydrogen can come off. If you look at the acetate ion, yeah, that's exactly what happened, is that hydrogen came off. So let's look at why it would come off. See these three hydrogens over here? Those are the ones that are not put in front. You know why? Because they're not reactive hydrogens. Why are they not reactive? Because they're stable. Why are they stable? Because the difference in electronegativity over here is only about 0.35. These are non-polar covalent bonds. So those atoms are sharing the electrons fairly equally. Everybody's happy. But look at the acidic hydrogen over here. Again, it formed that bond with the oxygen because it wants to become 1s2. But instead, it finds that its electron is actually being pulled away by that mean, selfish oxygen. So what is that hydrogen looking for? Happiness. And for a hydrogen, happiness means 1s2. So it's looking for 2 electrons to call its own. And every time it turns around, it's bumping into a water molecule. Look at all those electrons on the water molecule that the water's not even using. So every so often, it basically jumps ship. form hydronium ion, and you form the acetate ion. Okay. So one of the polyatomic ions that's not normally in a textbook that I added was oxalate. Because especially in Hawaii with taro and starfruit and other things like that, we have a lot of oxalate in our diet, potentially. And that's one of the things that forms kidney stones and things like that. So, yeah. So here's the carbonate ion, sulfite and sulfate. Basically comes from fossil fuels. So if you take fossil fuels, biomass was simply mostly plant material, a little bit of animals, and then it got buried and turned into essentially oil and coal and things like that over a process of millions and millions of years at very high temperatures. So now we dig it up out of the ground. We go all over the world digging this stuff up and burn it. So when you burn fuels that have sulfur in it, you will oxidize them all the way to SO2 and SO3. And what happens is it combines with water to form the acids. So if you burn fossil fuels, or if you've ever been to the volcano and it's erupting, you can smell the sulfury smell. You're smelling SO2 and SO3. So it comes down as acid rain, and that basically destroys plants. It does all kinds of different problems, right? But the other thing it does is it weakens the new lava flows. It acidifies and weakens the new lava flows so that plants can get, I don't want to say a grip on the soil and start to grow. Anyway, so what do acids do? They give off hydrogen ions. So here we have sulfurous acid. Take off a hydrogen, you get hydrogen sulfide. Take off another one, you get sulfite. H2SO4. Take off one hydrogen, you get hydrogen sulfate. Take off two, you get sulfate. This is where they come from. So here are the Lewis structures of these. Okay. And oftentimes textbooks ignore sulfite. Sulfite is extremely important to know about. A lot of people get allergies to sulfites because they put sulfites into salads and stuff like that at restaurants. I'm not sure we have restaurants anymore, do we? Anyway,
No.
sulfite can be oxidized into sulfate. I showed you that right here. So here's aluminum sulfite and aluminum hydrogen sulfate. So I did the same thing for phosphite and phosphate. And I should point something out to you. This is why it's difficult for a student to go online and just try to find things out on their own, because everything is so different. The way that we are doing Lewis structures, you would draw phosphate like this. But most biochemistry textbooks will draw phosphate like this. And both of these are correct. If you look at them, both of them have 4 regions of electron density. Both of them would be tetrahedral. So there is no machine that can tell us which one is correct. So the answer is they're both correct. But the difference is this does not meet the octet rule, and this one does. So in terms of teaching, if they start doing this stuff, they're undoing all the things that they're trying to get you to learn. And this is one of the biggest problems with education. If you're going to teach students something, you have to be consistent. Consistent, consistent, consistent. If I show you the same thing 3 times in a row, then on the 4th time I show you something that doesn't jive with that, you're going to be totally confused and and you feel like you don't know anything anymore. And that's what happens to you when you start roaming around on the internet, unfortunately. Let's see. So you see kind of what I'm talking about, right? Just trying to give you an idea of things, and you see lots of Lewis structures and you learn from that. So here's cyanide. Cyanide was the suicide pill, right? So say you're a spy and you get caught by the enemy government. What are you supposed to do? Take that suicide pill and just die. Or you don't take that suicide pill and you think to yourself, oh, I could maybe work for 2 governments. Become a super spy, double your income. So your choice would be double your income or die. Anyway. So notice the iron 2 right here. Iron is in group 8. So iron, the element, has 8 dots around it. When you form the +2, you lost 2 valence electrons, right? You lost 2 dots. You still have 6 left over. Or no, what did I put there? 2, 4, 6, yeah, 6 left over. Okay. And here's one of the rare cases where we have a triple bond. So if you actually take the formula for cyanide and do its Lewis dot structure, the only way to meet the octet rule for those atoms is to have a triple bond. Okay. So you guys know what lemurs are? Yeah. Well, they're extremely endangered primates. They're actually primates. And there's one of them, like if you have a whole bunch of different primates living on small or not a very diverse ecosystem like Madagascar, the different types of lemurs specialize in eating different parts of the same plant. So bamboo contains cyanide in it to protect it from predation. So this particular one eats the fresh bamboo shoots and it consumes enough poison to kill 10 of them. But how it gets around it is that before it eats the bamboo, it goes to the bottom, goes to the floor of the forest and eats clay. It eats dirt. Because in the dirt, there's these iron that will chelate out the cyanide. So when it's in this form right here, it cannot be absorbed by the intestinal cells. So it simply passes right through the lemur and the lemur doesn't get affected. If that lemur did not eat the dirt before it ate the bamboo, it would be dead. But the problem is you come up with some scary colored eyes. By the way, humans, dogs, a lot of social animals, why is the bulk of their eyes white and then the iris dark?
Showing health.
That's right. Because the other member of your species can see where you're looking, learn about your emotional state and all that kind of stuff. If you look at an animal like this lemur right here, it doesn't have that because it's not that kind of a social animal. And here's some super wild polyatomic ions. So many of these are actually very dangerous. Your own body produces superoxide and many other radicals over here. So, yeah. Here's the bleaches. And I put a little diagram here. How do the bleaches work? So say X is your stain. What a bleach will do is put oxygen on that and oxidize that molecule. That will destroy the color and oftentimes make it more soluble so it can be washed away. So here's the series of 4 chlorine bleaches. Clorox is hypochlorite. It's the weakest of the chlorine bleaches. Why would this one be the strongest? Because it's got a lot more oxygen to put onto some other molecule. But Clorox, by the way, is a very dangerous substance, and you need to treat it with caution. It is the weakest of the bleaches, of the chlorine bleaches. The non-chlorine bleaches are mostly peroxides, like hydrogen peroxide. Okay. This is all more Chuck Norris jokes. Okay. So by the way, I got an email about an hour before we started about the peer tutors at KCC are available online. Did you guys get that email?
Yeah.
You did? Okay.
Yes.
You might want to try that. Okay. So here's the dilemma I always have, right? I go to give a lecture at KCC, and most of the students haven't read the material. They're just sitting there, not knowing anything, and then listening to stuff that they don't have a way to organize it in their head because they never read anything. It seems kind of like a waste of time. So I've always dreamed of different ways, better ways to do things, but we don't really have the facilities. What I would like to do is take all 5 of my classes, or however many are the same, and I do one lecture in a big lecture hall. Then the rest of the lecture periods I spend doing something like this. It's basically it's a review. But if you haven't read the material or engaged in the work in any ways, I don't see what you're going to get out of this, or out of a lecture, out of anything. See what I'm getting at?
Yes.
So,
Yep.
So anyway, what I would like to do is do another one of these on Wednesday. Did you think that you benefited from this?
Yeah.
Yes.
Yeah,
Mhm.
Okay.
we need you.
Yeah. That's what my grandkids say. Especially if you have them in Target, right? And you got to spend all this time at the, yeah. So my 4-year-old granddaughter, we were in Target, and she's like, I want every single one of these dolls, all of them. Okay. So anyway, we have I'll look at what the chat has, make sure I didn't miss anything. And if you guys think of anything to make it better, email me or anything like that. And I really wish you guys would use the discussion on La Lima to talk to each other and to ask questions. I look at it every night. I probably look at it 10 times a night, and then there's nothing there. I have a bunch of antisocial stuff. That's the problem. Okay, so we'll do this again on Wednesday, and we'll start with chapter 12, yeah?
Okay.
And then I had to re-upload the chapter 12 video to YouTube because it only had the second half of the video. It didn't have the whole thing, so now the whole thing is there. So, sorry. Does anybody have any other questions?
Is this recorded on someplace where we can review it or no? Because this is recorded on my screen.
I don't know if I recorded it or not. I was so busy trying to get the screen sharing to work.
I
Not
think
knowing
you are recording. It says on the right upper hand corner, there's like a little record. I don't know if that means recording.
Yeah, that's what I'm saying too, but
I think he recorded. I think he's recording.
so where would we be able to see the recording?
He would have to post it.
Yeah,
Yeah.
that's another issue.
Yeah, my
Or
other
Google there.
professor,
Yeah,
he posted on, oh, well, he posted it on YouTube, but you have to have like a link to get to it, so you can't like search it. So kind of like how yours is.
Yeah. Well, I'll have to find out where on my computer this thing gets saved. That's the light right there.
Talk to your colleagues. Don't be antisocial.
Yeah. It's funny, I spent so much time on Zoom the last couple of weeks, but I never had to run it, you know what I mean? So, but it works really well. It's just really amazing. So I was on Zoom with a bunch of people from Maui College this morning, and yeah, it works really well. Okay, so if you got more questions, you can save them till Wednesday or email me or post it in discussion and all that stuff. And well, only exhale, don't inhale.
Is it the same time? Like
Yeah.
2 o'clock?
And the other thing too that people don't realize is that, you know, you watch me and I'm watching you, we're constantly touching our face, right? So I come into the biomed building, and I know everybody in this building is supposed to be scientist types, but I gotta put my hand on the handle to open up the door. I'm like, I don't want to touch that. I get into the elevator and I gotta push the button. I don't want to touch that. And then everything you touch ends up on your face.
Bring Purell with you all the time.
Yeah. So you're gonna get the virus through your nose, your eyes, your mouth. Right? So just be cautious of that. So I will see you on Wednesday.
Okay.
Thank you, Professor.
Thank you.
Yeah.
Bye.
Bye.
Bye.